Picture a scatter of red dots on the left and blue dots on the right, floating on a flat plane. They belong to two different groups, and for now they sit comfortably apart. Our whole quest today is deceptively simple. Draw a single line that keeps the reds on one side and the blues on the other. At first this feels trivial. Of course you can slip a line between two groups that don't overlap. But hold that thought, because the interesting question is not whether a line exists. It's which line out of infinitely many we should actually choose. Watch what happens when I try a few different lines. Each one still separates the colors perfectly. This one tilts left, this one hugs the reds, this one leans toward the blues. All of them get a perfect score on the data in front of us. So if every one of these lines is correct, what makes a good separator different from a merely acceptable one? To answer that, we have to think about the points we haven't seen yet, the future data that will arrive tomorrow. Here's the danger. If a line squeezes right up against the red points, a new red point that lands just slightly further out could fall on the wrong side. A line that crowds one group is fragile. It has no room for error. This suggests a beautiful principle. The best line isn't just one that separates the data, it's the one that stays as far as possible from both groups at once. We want breathing room on every side. Let me make that idea physical. Instead of a thin line, imagine we're paving the widest possible street straight through the gap between the two neighborhoods. The street can't touch any house on either side. Our line will run right down its center. Now the goal has a wonderfully simple shape. Widen the street as much as you can. Push both curbs outward until they can't move any further without bumping into a data point. The wider the street, the more confident and robust our separator becomes. Here comes the key derivation. Exactly how wide is this street? To measure the distance between the two curbs, we take any point on the lower curb and step across to the upper curb, always moving perpendicular, in the direction of W. The value of our expression has to change by 2 across that gap, from -1 all the way up to +1. And we know the expression changes at a rate given by the length of W for every unit of distance traveled along W. So the physical width of the street is that change, 2 divided by the length of W. Let that sink in, because it's the heart of everything. The width of our street, the margin, is simply 2 divided by the length of W. If we want a wider street, we need a shorter W. A big fat margin corresponds to a small vector W. So the entire optimization flips into something clean. Maximizing the margin is the same as minimizing the length of W. Mathematicians prefer to minimize 1/2 of the length of W squared, because it's smoother to work with. But it's the exact same wish, make W as short as possible. But we can't shrink W to nothing, or the street would swallow the whole plane and misclassify everyone. We need a constraint. Every single point must stay on the correct side of its curb, off the street entirely. We write that constraint compactly. For every point, its label times the expression W dotted with x plus b must be at least 1. Blue points land at +1 or beyond, red points at -1 or beyond in the negative direction. This one inequality keeps every point off the street and on its proper side. So here is the complete support vector machine stated in 2 lines. Minimize 1/2 the length of W squared, subject to the rule that every point satisfies its margin constraint, a tug of war between a short W wanting a wide street and the data points refusing to be crossed. This kind of problem, minimizing a smooth bowl-shaped quantity under straight-line constraints, is called convex optimization. It's a very friendly landscape. There are no confusing local traps, just one single lowest point, one best answer. That guarantee is a big part of why support vector machines were so beloved. The trick is this. If the data won't separate in 2 dimensions, lift it into a third. We're going to give every point a new coordinate, a height, and use it to hoist the inner points up out of the page while the outer points stay low. A natural way to assign that height is by distance from the center. Points near the middle get a small height, points far out get a large height. But let me use the opposite convention that makes the picture cleanest. Let the central blue points rise high, and let the far red points stay near the floor. Watch the geometry transform. As the points lift, the central blue cluster floats up into a peak, a little mountain, while the red halo spreads out across the ground below. Something that was hopelessly tangled in the flat world has come apart in 3 dimensions. And now the miracle. In this taller space, the two groups are separated by something perfectly flat again, an ordinary plane. Slide a horizontal sheet between the elevated blue peak and the grounded red halo, and it cleanly divides them, a flat cut, just at a higher altitude. That flat plane in 3 dimensions is exactly the linear support vector machine we already know how to solve. All our machinery, the widest street, the support vectors, the short W, works perfectly, unchanged. We didn't invent new math. We just found the right space for the old math to work in. Now let's descend back down to the original flat page and see what that plane became. As we drop back into 2 dimensions, the flat cut casts a shadow, and that shadow is a curve. Specifically, it's a circle, wrapping neatly around the inner blue cluster. So by taking a stroll through a higher dimension, we conjured a curved boundary in the original one, something a plain linear classifier could never draw. The straightness lived upstairs. Down here it looks beautifully curved. That is the whole idea in a single picture. But here's the catch that makes this more than a party trick. Lifting every point into a higher space sounds expensive, and for really rich transformations the new space might have hundreds, thousands, even infinitely many dimensions. Computing all those new coordinates directly would be a nightmare. This is where the real magic word appears, the kernel trick. Look back at our optimization. If you inspect it closely, the data points only ever show up in one form, as dot products between pairs of points. The individual coordinates never appear alone, only these pairwise comparisons. That's the loophole. To run the machine in the lifted space, we never actually need the lifted coordinates. We only need the dot products between lifted points, and a kernel is simply a shortcut function that computes that dot product directly from the original points without ever visiting the high-dimensional space at all. It's like being handed the answer to how similar are these 2 points, once transformed, without ever paying to do the transformation. Popular kernels like the polynomial or the Gaussian radial basis function correspond to enormous, even infinite hidden spaces, yet each is just a quick formula on the original coordinates. So we get the best of both worlds, the expressive power of a wildly high-dimensional space, curved and flexible boundaries in our original picture, paired with the cheap, convex, well-behaved computation of a simple linear machine. We never build the big space, we only whisper to it through the kernel. Let's gather the whole journey into one breath. We wanted a separator, and we chose not just any line but the one running down the widest possible street. That width, the margin, turned out to be 2 over the length of W, so we made W small. The street was pinned by only a few support vectors, the hardest points on the border, and everything else could be forgotten. And when the data refused to separate, we lifted it into a higher dimension where a plain flat plane did the job, computing that lift for free with the kernel trick. What I love most is that it's all one idea wearing different costumes. A wide margin for safety, a sparse set of decisive points, and a clever change of space. Simple geometry, pushed relentlessly, becomes one of the most elegant classifiers ever invented. Thanks for taking the walk down the widest street with me. If this made it click, subscribe for more visual math.